All right, guys. What is the relation between, close your laptops for sure today, please, unless you're doing course material on them. What is the relation between, again, laptops, please? Close laptop. Laptop. Yep. What is the relation between S, R, and theta? S equals to theta R. Have you seen this before? Yes, where? If you have a circle, a full circle, we say the circumference of the circle is 2 pi r. Okay, guys? Why the 2 pi r is radius, fine. Distance, radial distance. The 2 pi is what? Is the angle that you cover sub 10 as you go around the circle. It's 2 pi. If it's 2 pi, fine, the circumference. If it's not 2 pi, you get S equals to theta r. Okay? Theta in radians. If I take the derivative with respect to time, what do I get? ds by dt is d theta by dt times r. So what is that? We call this what? This one. ds by dt, rate of change of s, as well as the tangential velocity or speed. Vt is equal to, what is the name for d theta by dt? What symbol do we use for that? Omega. It's equal to omega r. And if I take one more derivative, and it's d2s by dt squared, same as dv tangential by dt, that's the same number. That is equal to what? d2 theta by dt squared times r, or d omega by dt times r. What do we call this number? That is referred to as what? Alpha. So that becomes, that equation becomes, this guy is nothing but a tangential. A sub t, so your formula looks like a tangential equals to alpha r. Okay? Omega is the angular speed, and alpha is the angular acceleration. The units are radians, radians per second and radians per second squared, and they describe, well, angular position, or, change in angular position if you want, and then angular speed and angular acceleration. You don't measure them in degrees, you measure them in radians. So the SI system units for these things are radians. All right, so what are we talking about now? Guys, if I have a plane traveling at a given speed, up a given altitude, and I want to keep track of that plane, I don't have to go and say it went from point A to point B between these clouds. If it's traveling on a fixed trajectory for a while, I know how high it is. I don't have to worry about that. What I'm doing here will be the equivalent of me saying, I'm going to sit at the center of the earth and have a protractor and, trace the radius to that plane as the plane moves. I know how far it is. All I got to do is that it was here. I'll tell you that it moved by 2 or 3 degrees. Because it has a fixed height and a fixed radius from the center, I will know exactly where it ended up. So I'm monitoring really the angular position indicator on my protractor. And that will move at a given speed. That's how many radians or degrees per second. And if the speed changes, that gives me the angular acceleration. All the things that we've talked about for kinematics in one dimension apply to kinematics for rotation. Our kinematics equations, we have to now make the transition from, so delta x, from linear to angular variables. Delta x is equal to 1/2 a t squared plus v0 t, and that's it. The velocity equation was v is equal to at plus v naught. And finally, the time independent equation was v squared final minus V naught squared is equal to 2A dot delta X. These were vector equations, and what we're going to come up with is going to be more or less also vector equations with a bit of a twist. I'll tell you about the twist in a second. Guys, imagine now that we are doing this business of traveling on a straight line, but instead of going on a straight line, we're moving on the surface of a large object like Earth, for example. So the distance that I cover here, either called X or S, on some big object of radius r, I'd like to now be able to see what happens to the angular variables and not just the linear variables. What do I do to make the transition from translational to rotational variables? How do we do that? Anybody? It's in front of you. The tips are there. How do you go from x to theta? Yes? It's very, very, very easy. I divide by r. What is delta x divided by r? Delta theta. Delta theta, or theta minus theta naught, equals to 1/2. What is a divided by r over there? A divided by r gives you alpha. So that's 1/2 alpha t squared plus, well, v divided by r is omega, so omega naught t. Okay. The second equation is v divided by r will give me from here. Guys, these three equations are the main equations, or not main. We will be using them extensively over the past next 2 weeks. We have, this week we're focusing on rotation, and next week we'll have angular momentum and rolling motion. We have about 7 lectures of this. You really need to know these by heart, know them really well. V divided by r is omega, so omega final, or omega is equal to, again, a divided by r is alpha, alpha t plus omega naught. Now I'm going to put vector signs on these things, but please pay attention to the following. There is no ambiguity that alpha is a vector. It's angular acceleration is accepted to be a vector. There's no question. That guy, omega, is not totally a vector. It's known as a pseudo vector because it's obtained by a cross product, v cross r. You don't have to get into that, but it's not really called a vector. And this one is definitely not a vector. However, for our purposes, because it has magnitude and it has direction, we're going to put a vector sign on it. However, it's not entirely correct, right? You could use scalars for these things as well, which is probably a better approach, but we'll leave that on there for now. Keep that in mind going forward when you go to upper years, that delta theta is not entirely a vector. Okay, so this is okay for sure. And here I divide by what? R squared. V squared divided by r squared is omega squared final minus omega squared initial equals to 2 alpha, again, with a grain of salt, delta theta. That is questionable. That's not entirely true. Okay, so now we have gone from, okay, how did we get that? Divide by r squared. 1r goes here, gives me alpha. 1r goes here, gives me delta theta. So now we have our kinematics equations for rotation at constant acceleration. What have we done today? We've made the transition from tangential or linear variables to angular variables, and we've applied that transition to our kinematics equations for constant acceleration to end up with our rotational kinematics equations for a spinning or rotating object. Okay, we'll be using these in a couple of examples. But we need to get familiar with them. So guys, you need to, when you take them home today, please make sure you understand everything that they symbolize and how they can potentially be used. Again, we'll be using them extensively over the next little while. Any questions so far? Yes? Speak up, Tito. Yeah. That is just, this guy? No, that's tangential. That's your kinematics equation from God knows when. From 6 weeks ago. The object moving in a line, its speed along the line is given by that. What? Yes?
Could you go over the last one again? Why are you why?
That one? Here. Why that? Why this or why that? Are you okay with this formula?
Well, yes, that one, but not the...
Yeah. You divide by r squared, what do you get? What is v divided by r? Okay, we're using that. So instead of v divided by r, give me omega. Now it's v squared by r squared, give me omega squared. Again, this is the action that we have to take. This is not. We divide by r squared to obtain that. Okay? Is that cool? Tito, yes?
What if it was central?
We're not going into that right now. Just shake hands with me on this. We'll worry about that later. Okay? It doesn't apply this way. All right, guys. So, anybody else? Yes?
If you divide it by r squared, then how come that becomes alpha?
Magic. Divide r squared, one r here, one r there, alpha, delta, theta. Is that better?
So how come you're dividing only r on one side and r squared on the other?
Talk to him. Any Albertans in the room? Hicks. Redneck. Yeah. What? I'm from Alberta too. I mean, that's what I did in my army training. Yes. Yeah. No. What was the question? Sorry. Okay, quiet. Let us speak. Yell at me, please.
For the third rotational kinematics equation, we divided the entire thing by r squared, right?
Yeah.
But acceleration tangent divided by r squared isn't lambda.
It's messed up, man. Okay, buddy. How about I divide one last time? Please pay attention. If you're not getting this, by r squared means I divide this by r. I divide that by r. Is that okay? Will that work? That divided by r is what? Look over there. Alpha. Yeah? See me after. Or talk to him. Okay, so a plane. This is not entirely accurate because Earth is not totally a sphere between these 2 points, but we'll assume that it is. Let's say somebody takes off from Calgary, lands in Fort McMurray, 43 minutes later. Distance is 720 kilometers. What is the angular speed? Omega. So omega is what? Be easy, guys. Omega, assuming constant speed or omega average, is v divided by r. And the speed is 720 kilometers. That's 1,000. Divided by minutes, 43 times 60. Has to get to seconds. And you divide the whole thing by the radius. I mean, more or less what? 6,400 kilometers.
Why did you give us that before? Are we supposed to know that?
Well, I don't know about you guys, but us people on Earth know that this is usually, that's the radius of our planet, man. Yeah, you should know this. Earth's radius. Well, if you don't feel bad. But just double check where you came from. They have a different value there. All right, Mars or whatever it is. All right, 1 times 10 to the power 3. Okay, so whatever that is, okay, you guys figure it out. The units will be radians per second. Okay, that's just a little exercise in converting linear to angular, and you can do the same thing for alpha and theta. More importantly is the problem that we have, or the example we have next. You have a wheel that is spinning at 21 radians per second and is brought to a stop over 3 revolutions, okay? Assuming constant acceleration, how long did this process take of bringing this wheel to a stop? Please pull out your calculators, take a few minutes to do the problem, example, and then we'll take it up. Yes, we have a session this Wednesday at 7 o'clock, 7 to about 9, 7 to 8:30. And going forward, guys, we will, unless I say otherwise, we will be using for sure the last 2 lectures, makeup lectures. They'll be Wednesday at 4:30. Should I tell Diane? I'll let Diane know. All right. Yes?
Where is it?
Which?
The physics section.
The one on Wednesday?
Yeah.
Oh, I don't know. It's just Arts Lecture Hall 113 or 116 or whatever it was. I think we have, they told me about a date, one date that we don't have the room for. I'm worried it might be this, October 30? It can't be. I hope not. Anyhow, we'll check. We'll see. So again, guys, going forward, the makeup lectures are on. The ones that we have, I believe, Wednesdays at 4:30. So next Wednesday will be interesting for you. You see me 3 times. We have office hours from TA. Remember, guys, we have office hours with TAs and me today, and office hours tomorrow from 5 till 9 with the TAs. So just keep that in mind. No, for me, it's just Monday now until they're full. You know, when Monday fills up, then I'll open up Tuesday. Huh? Which one? Well, it was because we had no, there was a holiday on Monday. Okay, guys, we need the time. So time says what? Omega final equals to alpha t. That's the one with time plus omega naught. That makes sense to use because it has omegas in it. I have omega initial, I have omega final, and I don't have alpha. Okay, use the third equation. Says, please pay attention to how we use these now. Omega squared final minus omega squared initial is equal to 2 alpha dot delta theta. Please pay attention here, guys. Omega squared final to a stop is 0 minus 21 squared. That's equal to, well, guys, according to our kind of pseudo vector whatever thing that we're using here, this is 2. Okay, pay attention here, please. Which way is omega? Which way is omega? Well, that way, right? Which way is delta theta? Which way is the angle increasing? That way. Now, if alpha was in this direction, what will be happening to the wheel? It'll be speeding up, so alpha must be in the opposite direction. Alpha is that way, right? So, so basically, this is 2 alpha, which we don't know, okay, times delta theta we know is what? 6 pi. Okay? Now what am I missing here, guys? We are saying vectors or scalars that oppose one another, either or. We need one vector this way, one vector that way. We need the angle between them is 180, so we need a minus sign. So I have to have a -1. Right? Either because these are scalars that oppose one another, or because of the vector formulation, okay? We need a minus sign there, otherwise this will not work. So alpha is equal to 21 squared minus 21 squared divided by -2 into 6 pi. And that is 11.72. 11.69. 11.69 radians per second squared. Okay, having known this now, I go back and plug it into here. Please pay attention here too, guys. Here, guys, don't lose your beans. Don't lose. Keep your wits about you. Just because we're seeing rotation for the first time doesn't mean that we forget everything else. We have a vector equation and we have a magnitude equation. This is obviously not a vector equation anymore because this is not a vector. It's omega squared. This is not a vector. And this is the same as that equation here, right? That is not a vector equation. Here, we did not put signs as to positive and negative, up and down. It didn't matter because none of these were vectors to start with. However, for these guys, we always had to go and say that positive or whatever, right? For rotation, though, that does not make sense. We have a vector equation that needs a sign. What do you think is appropriate to indicate positive and negative? How can I do that? Yes? Yeah, you could do curvy arrow, and I will say maybe this is, this is positive, okay? And based upon that, then omega final is 0 equal to alpha. Well, I'm picking this to be positive. This means that omega initial is positive, but alpha is negative according to that, equation there. Therefore, that's negative alpha, which we know, 11.69 times t plus omega naught 21. So you have t is equal to 21, negative 21 divided by negative 11.69. And you figure it out. Okay, it says it's brought to a stop. So it has to what? Slow down. Okay. I can't see the alphas that way, let's say, okay? Let's see if I can play a different game. Let's say I put alpha that way. What do you think will happen now? The thing's gonna speed up. Right? I don't want it to speed up, it's gonna be the
direction of the acceleration.
That one.
Right, okay.
Yeah? Fair enough? What? You can do whatever you want. Keep it vector form if you want. That's fine too. But this is not what we've been doing so far. In keeping with what we've been doing, and also going forward to talk about the more complex problems that are going to come up in about 4 lectures, we will definitely be keeping our vector magnitude notation. You could do it in scalar magnitude notation as well. That's okay, but it's a bit less ambiguous with vectors. So this is really just in keeping with our vector practice. Okay? What? Back some questions somewhere? Somebody? Change your mind? What?
So for this rotation question, is velocity changing to omega and acceleration changing to theta and acceleration changing to alpha?
Yeah. Yeah, indeed. I need a volunteer. Yes. Well, eeny, meeny, miny, mo, catch that, but I know the talk. I'll go with that. He put his hand up first. You're both sturdy, but he's a bit more sturdy. Yeah. Face the class, go like this, please. I'm going to try to pull out a socket. No, he's not a zombie. Okay. I need to rotate his arm about his shoulder joint. Okay? So move forward a little bit. If I push here, he can stop me, no problem. Don't cooperate too much. Okay?
Okay.
And here, not easy. Now here, he has no chance. Why? Because, what's happening? What dictates, guys, the effectiveness of the force that I apply? Its effectiveness in causing a rotation depends on what? Distance, force. Okay, yeah. So how much force I apply, the distance from the pivot, and also what direction. So 3 things, okay? Direction, look at that. Now, I now have the distance advantage. I have the power. Right? Are you guys, who's seen He-Man? Yeah, you don't look old enough though. Hey, anyhow, so okay, guys. So I have the forces there, but also, you know, and the distance is there. But the problem now is that the direction is not there. I'm pushing in, trying to rotate. Okay, that socket will come out before it rotates. Let's see if it will. So, guys, three things dictate the effectiveness of a force. Torque is a measure of how effective a force in creating a rotation. It depends on three things: distance, angle, and force. Okay? Thank you. Thanks, buddy. All things the same. If I say, where is the center of mass of this beam? Where is the weight acting? Do I have to consider mg that part, mg that part, or can I just say it's right here in the middle and that's what mg should be? Okay. We're going to be moving towards dealing with objects this way. Okay. We are going to replace the object, if it's appropriate, and whenever it's appropriate, with a center of mass representation. We say instead of taking the mass, the weight to be here, there, that's the center of mass, and that's where the weight is acting. I want to, guys, if I left this beam, what do we call this, by the way? Anybody know? A free hinge. Free hinge means what? If you let the beam go, what will happen to it? Flop. It will fold like that. If I want to prevent it from falling, I'm going to apply a force here, F, at an angle of 32 degrees. And I'd like to see what this force is. Please take a minute to do that. So mg is that way, F that way. What do we say? In the end, we are not going to go into the formalism of torques and sign convention yet, but I will introduce it to you now. In about 7 lectures, we'll go fully into it for about a week or so when we do statics, structures and whatnot. Now, you say some of the torques about O is equal to 0. I don't want this to move, right? So the force will be whatever to keep this from falling. That's what we're looking for. This is point O. Sum of the torques is equal to 0. Torque of a force is defined as R cross F. And that, anybody know what this means? Implies that the magnitude of the torque, the magnitude is equal to R F sine, not cosine theta. R magnitude, F magnitude, sine, the angle between them. Now please pay attention to this sine theta business, okay guys? By physically or mathematically, the theta is taken in a specific way. You have to go with the first vector, which is R. Please pay attention. You go with the first vector, and you rotate this way, counterclockwise, till you meet the second. The proper theta we should be using is this one. However, to your advantage and good fortune, the sine of that one is the same as the sine of that one. So the rule is you go after the smallest angle all the time. Okay? You look at the smallest angle between the two. It should be, in principle, guys, one more time, it should be the theta should be R, F sine theta, theta going that way. Has to be, you go extend R, you fold back counterclockwise till you meet the second vector. That should be the proper definition of theta. However, for us, we will take the smallest angle between the two, and that's a lot easier. Okay, fine. This is a vector equation. What torques do I have? There is the torque of mg plus the torque of F as a vector must be equal to 0. All right, we have an issue now, guys. These are vectors, and we like to go from vectors to magnitudes. How are we going to do that? When we had forces, we picked, well, if you had forces, this is forces, A's and whatnot. You picked up as positive, or down as positive, or this way, or whatever, right? Okay. What do you do for rotations then? Cyclical arrows, okay? So you say, okay, fine. The action of a force, what does the force do? Translates you, moves you up or down. So you say, I'm going to pick up as positive or down as positive. That has no meaning here anymore. Because we're talking about torques. What do torques do? They twist, rotate. So rotation is important. in which direction is mg trying to rotate me? If I leave it to its own devices, it's the only force on the system, which way is the beam going to rotate? That way. And if you leave F alone without mg, that will rotate you that way. So the direction is now chosen by whatever. I mean, it has to be either this or the other one, other direction is positive. Having said so now, guys, you please, guys, I will repeat it to you in 7 lectures. This is something for the subconscious to think about, okay, for now, or to keep in the back of your mind. We're going to revisit it again, but mg points down. It doesn't matter which way they point. What matters is what are they going to do? Which way are they going to rotate me? Is mg rotating me in that direction or the opposite direction to that? That direction. So it should be a positive torque. The torque of mg is, not mg is positive, the torque caused by mg is positive, minus the torque caused by F, that's equal to 0. So what I need, and you could have told me that already, guys, is that the torque of mg be equal to the torque of, well, let me, before we do that, okay, what is the torque of mg equal to? Well, torque of mg is a force acting at a distance. Its torque is given by Rf sine theta. Okay, what is R? L over 2 times the weight, which is mg, multiplied by the angle between them is sine of 90, which is 1. Right? So that's 1. Okay, minus the torque of the force, torque of F. What is that? The distance is, the full distance is L multiplied by L multiplied by F multiplied by sine of 32 equal to 0. Okay? So, no, not yet. So F then is equal to, guys, F would be equal to, you bring it there, you say divide by L, whatever, mg over 2 sine of 32. Okay? So the force is given by that. Yes? So guys, what I need from you, or what I want from you, expect from you, is today we have made the transition from linear to angular variables. Please take that home and make sure you understand everything we did today. Going forward, on Wednesday, we're going to go into full rotational dynamics, not just kinematics, the version of Newton's law for rotation. Torque equals I alpha, moment of inertia and stuff like that. You need to have these basics at 100% before we move on, or before you move on. So you need to have the basics before we move on, guys. But please keep in mind that we've made the transition from, we're going to be doing rotation for about 2 weeks now, straight, about 3 weeks actually, if you count statics. Okay. This is the first representation of torque. There are 2 more ways of looking at torque that I'd like to take up with you. Second way, torque is equal to R cross F. That's the magnitude of the torque is equal to RF sine theta. Same formula, but just a different way of looking at things. If I have a massless bar and I'm pushing on it with a force F this way, then that force about O, this is F, and this is distance R. That force will exert a torque. The torque is given by torque about O, this example, is equal to R F sine theta. Guys, the force can be broken up into 2 components. One parallel, to the moment arm, and one perpendicular. So this is F perpendicular, and that's F parallel. Think about this for a second now. Which component is it going to cause the beam to rotate, if it will? So this one doesn't count, and it shouldn't count. What we're going to do is focus on this product of F sine theta in this representation. And the F sine theta, if you look at this triangle, is nothing but the F perpendicular. So that's all that matters. That product then becomes R F perpendicular. Okay? That's what I'm going to drive home, is that the torque is equal to R. Instead of the full definition, the first way to see this is the full definition, RF sine theta. The second way, not definition, second way to look at the definition is R, the full distance multiplied by only the perpendicular component. Okay? The third representation, and they're all handy. They will all come in handy. They're all useful. For the third representation, please pay attention, guys. Again, we have torque equal to R, F, sine. By these, I mean magnitudes, okay? We're not going to write them again and again. How do you do this in the third representation? You probably have done this before. What you do is, please pay attention here for a second. This involves a bit of construction. You extend the line of action of the force, and you drop down a perpendicular to that line of action from the pivot. That angle is 90. R then can be thought of as a sum of two components, R perpendicular and R parallel. So now you say that what I'd like to do is, if this is angle theta here, then that will be angle theta there. What I'm going to do is focus on this product, the product of R with sine theta. And please observe here what that means. R is in this triangle. This is RR. The R sine theta, look here, guys. That's the 90. R sine theta is the opposite. So that reduces to what? To R perpendicular times F. This is the third way of looking at torque. They're all the same. They're all stemming from the same equation. Okay, once you have only in this third representation, you call this quantity, that guy, and that guy, you call this one the moment arm. The moment arm is only valid in this representation, and it means the perpendicular distance between the pivot and the force. So you have a force acting about a pivot, you find the perpendicular distance, and that is known as the moment arm. It could be a force or a component of a force. You break up a force into two components, and you find the perpendicular. For example, guys, this R, okay, this R is the moment arm for what? What is the moment arm for F here, about pivot O? Well, it's right there. This is the moment arm for all of F, right? What is the moment arm for this guy? You have to find the perpendicular distance, right? Break up force into two components, F parallel and F perpendicular. Where is the moment arm of F parallel? How do you do it? You stretch it back until you find a point to drop. That is zero. The moment arm of only F parallel is zero. What is the moment arm of F perpendicular? It's R. What is the moment arm of F? Itself. You have to drop it and find it that way. Okay? So please go over this stuff before Wednesday.